So today we're talking about differentiability, which means can you take the derivative? Um, and I guess I want to start with some bell work. Specifically, if the limit as x approaches a from the positive of f equals the limit as x approaches a from the negative of f, what can we say? What do we know because of that statement? Well, because of this statement, we know that the limit as x approaches a of f exists and is equal to the limit as x approaches a from the positive, which is equal to the limit as x approaches a from the negative. So, 1, we know existence. 2, we know it has the same value as those two limits. Okay, and then I would describe this in words how? Well, based on that statement, I would say the y values of f are approaching the same, I guess I want to say number, I really want to say y value, as x approaches a. Okay, so the limits from both sides exist. We know that the limit at the point exists, and we know that that limit at the point is equal to the limit of these two one-sided limits. So next, what can we say if this is true? What does this mean? Okay, so like the last problem, I could say, well, if these are equal to each other, then the limit as x approaches a of f prime exists and is equal to the limit as x approaches a from the positive side of f prime, which is equal to the limit as x approaches a from the negative side of f prime. Well, what does this actually mean? What does this notation mean? We saw when we had the limit of f, we were talking about the y values. What are we talking about here? Well, what we're saying here is the limit of the slopes of f are approaching the same y value as x approaches a. Okay, so this notation says that the slopes from one side equal the slopes from another side. Whatever that slope is, we're approaching the same number. All right, so there's our bell work. Next, differentiability. In order for a function to be differentiable at a point x equals a, and differentiable, well, that's able to take the derivative. In order for a function to be differentiable at a point x equals a, two things have to be true. One is f must be continuous at x equals a. And second, we need the limit as x approaches a of f prime to exist. Now, what's required for that limit to exist? Well, what this implies is the limit as x approaches a from the positive side of f prime equals the limit as x approaches a from the negative side of f prime. If the limit of the slopes is the same from both sides of that point, then the limit of the slopes exists at that point. So we need these two pieces of information, but generally we look at these two, because this will tell me this. Okay? All right, so let's if that's what differentiable means, what about things that are not differentiable? Well, we could have a thing where the function is not continuous at x equals a. So, not continuous. It could well be that the slope here on this side and the slope here on this side are the same slopes. So the limit of the slopes might exist, but the function is not continuous, and therefore no derivative is possible there. Okay, we could also have something like this, where the function is continuous at x equals a, but the limit of the slopes from one side doesn't equal the limit of the slopes from the other side. Because the limit of the slopes are two different numbers, we say no derivative possible at that point. This is sometimes called a corner. And a more extreme corner, when the slopes aren't just different, but one is positive infinity and negative infinity, looks like that seagull drawing I drew in elementary school. And this is actually called a cusp. And a cusp has the property that the limit as x approaches a from the negative side of the slopes is negative infinity, not negative 8, and the limit as x approaches a from the positive side of f prime, I have positive infinity. It's just an extreme corner. But here's what you can't do. You can't justify differentiability or not differentiability. You can't justify that there's no derivative here or no derivative here simply by saying there's no derivative here because there's a corner, or there's no derivative here because there's a cusp. That's not sufficient. That doesn't explain why not. And what we need to see is this. We need to see that the limit of the slopes from both sides is not the same. We need to see the limit of the slopes from both sides is not the same. In fact, if you didn't want to say this notation, you could say the limit of the slopes is not the same. Uh-oh, wait a minute. There's a lot of imprecision here. What the AP reader reads when you write this on your test is the slopes of what? The slopes of f, the slopes of f prime, the slopes of that giraffe's neck. What slope are we talking about? So that's not clear. And the slopes aren't the same where? Where aren't the slopes the same? Because it could well be that the slopes are the same at lots of other places, but you're not telling me anything about where the slopes. So you probably want to say the limit of the slopes of f are not the same at x equals a. And now you've said so many words with English that really it would be much less work just to say not differentiable because the limit as x approaches a from the negative side of f prime doesn't equal the limit as x approaches a from the positive side of f prime. That's it. I mean, look, it's got the clarity. It's the limit of the slopes of f, and it's as x approaches a. We've included all that information with our tidy, concise notation, which, if you tried to write as English sentence, you'd probably leave out some of that information. So I strongly recommend you describe, I can't take a derivative at a point for this reason, or because the function is not continuous at this point. Those are our two reasons for not having a derivative. Well, there's also an undefined derivative. So y equals cube root of x. This is actually a vertical slope here. And so the derivative isn't going to exist. The function is continuous. The limit of the slopes are approaching the same thing. The limit of the slopes, limit as x approaches a from the negative of f prime is infinity, and the limit as x approaches a from the positive of f prime is also infinity. The limit of the slopes are both approaching infinity as x approaches a. You could make the argument that you should be able to take the derivative here because these are approaching the same value and the function is continuous. And sure, except that I can't take the derivative of a vertical line. So I just have to know that this is an undefined slope on f at x equals a. Okay, so let's, there's actually something I want to bring up with you. If I know a function is differentiable, not only do I know the limit as x approaches a of f prime equals the limit as x approaches a of f prime, but also that f is continuous at x equals a. And remember, our definition of continuous was that the value of the point equaled the limit at the point on that function. Okay? So we can say differentiability implies continuity. Sometimes College Board likes to ask the question, is this function continuous at this point? And in the stem of the problem, they told you the function was differentiable. And so what you're supposed to say when they ask, is this function continuous? You're supposed to say, oh, well, because this function is differentiable, we know that this function is also continuous at that point. Okay, but what about reading this statement the other way? Does continuity imply differentiability? Is everything that is continuous also differentiable? Can you think of an example that wouldn't be? Draw it, and gosh, I wish we were in a Zoom so I could see it. That's right. I think about y equals absolute value of x, which is certainly continuous at x equals 0, but not differentiable, because the limit as x approaches 0 from the negative side of f prime, and the limit as x approaches 0 from the positive side of f prime, the limit of the slopes, they're not the same. And so this function, while it is continuous, is not differentiable. So we can say that differentiability implies continuity But continuity does not imply differentiability. We also need to know that the limit of the slopes is the same. And if they're not, no, even if we're continuous, we're not differentiable. Hey, speaking about differentiable, so, y equals absolute value of x. That's not differentiable at x equals 0, and we know that, right? So try this out. This is great. We'll pull out our calculator, and we'll take a little look-see. Okay, so I'm going to put in absolute value of x. That's math, number, absolute value, x. Okay? And zoom 6. I thought I did zoom 6. There we go. Okay, so now let's ask the calculator what the derivative is at x equals 0. Second, calculate, dy dx. That is my first curve, yes. Wait, did I press the wrong thing? There's no second curve. I must have pressed the wrong thing. Second, calculate dy dx. Okay, and where do we want to know the derivative? You actually have to put in the point and then hit enter. Hey, see what it says here? dy dx equals 0. Wrong way. It says dy dx equals 0. Says there's a slope of 0 there. How about second calculate? No, that was the one I did. Is it under math? Yes, nderiv. Let's try nderiv now. Nderiv, math, absolute, x, close parentheses, comma, x, comma, 0. I want to know about the slope at 0. And look, it says slope of 0 is 0. That's kind of funny, isn't it? The calculator thinks absolute value of x at x equals 0 has a slope of 0. Is that true? There's absolute value of x. And what do we know? Well, if we wrote absolute value of x as a piecewise function, it would be negative x for x values less than 0, and it would be positive x for x values greater than 0. And you could choose whichever one of these you want to put the could be equal to, because the limit of the function is the same at that point. Okay, but look here, what's the slope of this line? The slope of this line is negative 1. What's the slope of this line? Positive 1. Is it true that the limit of the slopes as x approaches 0 are the same as x approaches 0 from the negative? No, the slope here is negative 1 and the slope here is positive 1. So why does the calculator think that the slope at this point is 0, whether we ask it from the graph or using nderiv? And the answer is because the calculator is actually using symmetric derivatives. Right, symmetric derivatives. What the hell are those? Well, they're doing one-sided derivatives. They're finding the slope on this side, they're finding the slope on this side, and then they're averaging those two slopes. If I average these two slopes, yeah, I get 0. But that's, while the symmetric difference quotient is usually a great way for calculators to deal with issues, calculators will always report the wrong answer if you try and find the slope at a place where you know the function is not differentiable. Okay? So watch out for that on your calculator, and remember you're supposed to be able to do a number of things with your calculator. 1, you should be able to graph a derivative, and 2, you should be able to compute a derivative. Okay? All right. So, I want to do a little more practice of that stuff we were doing in the last video where we looked at, and it was differentiability, we look at whether or not a function was differentiable at a point. And so let's take a look at our one-sided derivatives again. And they're one-sided derivatives because we're going to be dealing exclusively here with piecewise functions, and we take the derivative of each piece at the point of intersection of the pieces. We're getting one side of that point of intersection or another, or maybe it's not even a point of intersection. Maybe the functions aren't continuous, in which case we already know that the function will not be differentiable. Okay, so I've got x squared minus 2x plus 3 for x less than 2, and 2x minus 1 for x greater than or equal to 2. So I want to know f prime of 2. Well, first, let's determine if f prime of 2 exists. What were the two things we said, again, at the top of this video that we need? F must be continuous. At x equals 2. Well, are we? F of 2 equals 3. Does the limit as x approaches 3 of this function also equal 3? Well, let's check the limit of each side. We know this is equal to 3 when I plug a 2 in, but what about up here? 2 squared is 4, minus 2 times 2 is 4, plus 3 is 3. Oh yes, that is true. Since the limit as x approaches 2 from the positive side of f equals the limit as x approaches 2 from the negative side of f, and these limits equal 3, we can say the limit exists on the function at that point and is also equal to 3. And since that limit of the y values is equal to the value of the point, we know that the function is continuous at that point. Well, what's the other thing we need for differentiability? We also need to know if the limit of the slopes are the same. So let's use our limit definition of the derivative to find the slope at x equals 2 for each piece. So how about the limit as h approaches 2 from the negative side of 2 plus h squared minus 2 plus h plus 3 all over h. So that's going to be the limit as h approaches 2 from the negative of 4 plus 4h plus h squared minus 4 minus, make sure you distribute that, to h plus 3. Oops, I only did part of it. This is just, I also need to subtract f of 2. And f of 2 is 3. Okay. So, and all of that's over h. Well, we see a lot of canceling here. This 4 cancels that 4, this 3 cancels that 3, and we can do some combining here. So we're going to have the limit as x approaches 2 from the negative side, 2h plus h squared over h. Well, that's much tidier. And I can even factor an h out at the top and say the limit as x approaches, no, h approaches 0, silly me, of h 2 plus h over h. These cancel. I can plug in my 0, and I get the limit as x approaches 2 from the negative side of f prime to be 2. The slope is 2, and I plug a 0 in there. Okay, well, what about from the positive side? So the limit as h heads to 0 of 2 plus h times 2 minus 1 minus 3, right? Because that's f of 2. I feel like I should really just write out what I'm doing and then do it. So I'm using h approaches 0 of f of a plus h minus f of a all over h. This is the one that I'm using in this problem. This is the limit definition of the derivative that I'm using in this problem. So I'm going to say then that the limit as h heads to 0 of 2a plus h minus 1, that's f of a plus h. No, that's a 2 because we're doing 2. Minus f of a. And since our a value is 2, 2 times 2 is 4, 4 minus 1 is 3. All over h. And so what does that give me? That gives me plus 4, minus 4, those cancel. And then I have 2h over h, and so I end up with 2. It's the limit as h heads to 0 from the positive. 4 plus 2h minus 4 over h. So those cancel, these cancel, and I get 2. The limit as x approaches 2 from the positive side of f prime is also equal to 2. So I know this function is differentiable at x equals 2. So f prime of 2, what's that equal? Sure, f prime of 2 is equal to 2. And can you explain why this function is differentiable at 2? F prime of 2 exists because f is continuous at x equals 2, and the limit as x approaches 2 from the positive side of f prime equals the limit as x approaches 2 from the negative side of f prime. We're talking about the limit of the slopes being the same from either side of this point on this function, and we also know that this function has to be continuous. Okay, so now it's your turn. How about this one? F of x equals x squared for x is less than or equal to 1, and 2x for x is greater than 1. We determine if this function is differentiable at 1. And if it is, tell me what f prime of 1 equals. Okay, I'd like to know what f prime of 1 is, but first you have to figure out, is this function differentiable at 1? Why don't you pause the video, give it a try, and come back when you're done or you have questions. You will need to do this on the Chapter 3 test, so please don't run away from it. Hiding from it is not going to help you learn how to do it. Okay, so we want the limit as x approaches 1 from the positive side of f prime to equal the limit as x approaches 1 from the negative side of f prime. So I need to find the limit of the slopes from each side. Okay, so from the left, I'm going to say the limit as x approaches 1 from the negative of f of x minus f of 1 over x minus 1. And so that's going to be the limit as x approaches 1 from the negative of x minus 1, x plus 1 over x minus 1. And once these cancel, I can plug my 1 in, and I get a value of 2. Okay? So I know the slope on this side approaching 1 is 2. Well, what about the slope on the other side? What about the limit as x approaches 1 from the positive side? Well, f of x minus f of 1, I plug a 1 in there and I get 2 over x minus 1. And so now I've got the limit as x approaches 1 from the positive. And again, I get 2. So I know that the limit of the slopes is the same from both sides. So does that tell me then that the slope of f at 1 is 2? Well, no, because remember there's a second thing we need to check. Not just the limit of the slopes, but also, what was the other thing? Right, the function has to be continuous. So, is this function continuous at x equals 1? Does f of 1 equal the limit as x approaches 1 from the positive side equal the limit as x approaches 1 from the negative side? Well, f of 1 is found by plugging a 1 in there, and that's equal to 1. And the limit as x heads to 1 from the positive side, that's this. And if I plug a 1 in there, I get 2. They're not equal, so this function is not continuous. This function is not continuous at x equals 1, so f prime of 1 does not exist because f is not continuous at x equals 1. Okay, and think about this graphically. You've got parabola to 1, it goes to 1, 1, and then you've got this linear equation, but if I plug 1 in there, the value is 2. They may have the same slopes. I guess I want something a little steeper over there. They may have the same slopes as we approach 1 from both sides, but since the function is not continuous, we can't have a derivative there. Okay, how about this one? F of x equals x squared for x less than or equal to 1, but now we have x for x greater than 1. Is f prime of 1, does f prime of 1 exist? And if it does, what's its value? Why don't you pause the video and try this one? Okay, welcome back. What did you come up with? Is this function continuous? Well, a limit as x approaches 1 from the negative side of f of x is 1 squared or 1. F of 1 is 1 squared or 1. But what about the limit as x approaches 1 from the positive side of this function? Well, if I plug a 1 in there, I get 1. And since the limit from both sides of f is equal to 1 at x equal to 1, and that limit is equal to f of 1, we know this function is continuous. So we've got one of our requirements. F is continuous at x equals 1 because f of 1 equals the limit as x approaches 1 of f. All right, so what's the other requirement? Well, the other requirement is to talk about the limit of the slopes. So if I do the limit as x heads to 1 from the negative side of f of x minus f of 1 over x minus 1, this is going to be the limit as x approaches 1 from the negative side, x minus 1, x plus 1 over x minus 1, those cancel, I plug in my 1, and I get 2. So I know the slope on the left side is 2, but what about the slope on the right side? What can we say about the limit as x approaches 1 from the positive side? Of, what do we want that limit of? We want x minus 1 over x minus 1. I'm doing f of x minus f of 1 over x minus 1. And that turns out to be 1. These aren't equal. And since they're not equal, the limit as x approaches 1 from the positive side of f prime does not equal the limit as x approaches 1 from the negative side of f prime. This slope is 2, this slope is 1, so even though the function is continuous, f is not differentiable at x equals 1 because the limit of the slopes from both sides is not the same. All right, well, if you have more questions about this, please ask them. Ask them in our Zooms, ask them on the group main. Get your questions answered. Don't fight for ignorance. When you have a question and you don't ask it, that's you fighting to be ignorant. Don't do it, please. All right, that's it for this video. I hope you have an easier time with differentiability because of it. Take care, everyone.